Hello everyone. I am Professor Lee from the Communication Engineering Teaching and Research section at Wuzhou University. Welcome you to this mini lecture. In the previous two sessions, we introduced the part on continuous time signals. Today we will cover Chapter 2, Section 3, the time domain description of basic discrete time signals. First, let me outline the two parts we will study in this session. In Part 1, we study the representation of discrete time signals. In Part 2, we study basic discrete time sequences. When studying discrete time signals, we should learn them in parallel with and by comparison to continuous time signals. Part 1, the representation of discrete time signals. We will use a discrete sinusoidal periodic sequence for illustration, and we denote the discrete independent variable by k. The plot enumerates the function values at points from -2 to 4. Here k takes integer values. The list representation of the sequence is written in a set-like form. We note an arrow above 0, which indicates a position k equals 0, with -1, -2 to the left in order, and +1, +2 to the right in order. Part 2, basic discrete time sequences. We will mainly explain 5 types of sequences: real exponential sequences, imaginary exponential sequences, and sinusoidal sequences, complex exponential sequences, unit impulse sequences, and unit step sequences. First, the real exponential sequence. The expression is shown in the figure, where k is a positive integer and r is the base. The plots below correspond to 4 cases: are greater than 1, are between 0 and 1, are less than -1, are between -1 and 0. When are greater than 1, the sequence exhibits exponential growth, with the sequence values increasing rapidly as k increases. When are between 0 and 1, the sequence exhibits exponential decay, with the sequence values decreasing rapidly as k increases. When are less than -1, the sequence exhibits oscillatory growth, with the sequence values increasing gradually while oscillating as k increases. When are between -1 and 0, the sequence exhibits oscillatory decay, with the sequence values decreasing gradually while oscillating as k increases. Imaginary exponential sequences and sinusoidal sequences have expressions as shown in the figure. In the expression of the imaginary exponential sequence, e is the base of the natural logarithm, j is the imaginary unit, omega 0 is the angular frequency, and k is a discrete time variable. In the representation of the sinusoidal sequence, a is the amplitude, omega 0 is the angular frequency, phi is the initial phase, and k is a discrete time variable. Using Euler's formula to relate the sinusoidal sequence to the imaginary exponential sequence yields the 3 qualities labeled 1, 2, and 3. For the complex exponential sequence, we discretize the complex exponential signal from a continuous time case. The derivation is shown in the figure, whose lower panel depicts a decaying sinusoid and a growing sinusoid. When are between 0 and 1, it represents a decaying sinusoid, whose amplitude decreases over time. When are greater than 1, it represents a growing sinusoid, whose amplitude increases over time. The sinusoidal oscillation further reflects the periodic variation of the signal, using points and curves. The plot intuitively shows how the complex exponential sequence changes with different values of r. For the unit impulse sequence, the value is 1 at k equals 0, and 0 for all other positive integer values. In the plot, only the function value at 0 is 1, and all others are 0. When the unit impulse sequence is shifted by n units, the function value is 1 at k equals n and 0 elsewhere. The role of the unit impulse sequence is that an arbitrary discrete signal can be represented as a weighted sum of shifted impulses. Taking the figure below as an example, at m equals -1, shift left by 1 unit with amplitude 3. At 0, no shift with amplitude 1. At 1, shift right by 1 unit with amplitude 2. At 2, shift right by 2 units with amplitude 2. The corresponding expression is shown in the figure. The unit step sequence uk is a discrete time sequence defined by uk equals 1 for k greater than or equal to 0, and u of k equals 0 for k less than 0, where k takes integer values. The plot is shown on the right. In the plot of the unit step sequence u of k, there is a step at k equals 0 that jumps from 0 to 1 and then remains with that value. In discrete time systems, the relationship between the unit step sequence and the unit impulse sequence is a cumulative sum. Specifically, u of k can be expressed as the sum over all delayed unit impulse sequences delta k minus m from 0 to infinity. In continuous time systems, the step signal and the impulse signal are related via calculus. Let n equals k minus m. So when m equals 0 and equals k, when m goes to infinity and goes to negative infinity, the summation from k down to negative infinity can equivalently be written as the summation from negative infinity up to k. Meanwhile, the unit impulse sequence delta of k can be defined as u of k minus 1, i.e., the difference between two adjacent terms of the unit step sequence. For the rectangular sequence Rn of k, the expression specifies its value is 1 for k in the range 0 less than or equal to k less than or equal to n minus 1 and 0 elsewhere. A rectangular sequence Rn of k equals the difference of unit step functions, representing a rectangular pulse that lasts for n units starting at 0. A rectangular sequence Rn of k also equals the sum of unit impulse functions. That is, the cumulative sum of the unit step sequence as k runs from 0 to n minus 1. This indicates that there is a unit impulse at each point. The specific expression is given in the figure. The ramp sequence Rk is a basic discrete time sequence defined as shown in the figure, where u of k is the cumulative sum of the unit step sequence. In the plot of the ramp sequence R of k, the horizontal axis is time k and the vertical axis is the sequence value R of k. The sequence values start at k equals 0 and take the value 0, 1, 2, 3 for an order after which the sequence remains the value 4 for infinitely many samples. In short, this kind of sequence is of significant importance in signal processing and time series analysis. Finally, please reflect on this lesson and complete the following exercises, which are intended to consolidate today's key points and further deepen your understanding. That concludes this mini lecture. See you in the next class.